Can anybody respond? How is the voice now, guys? Am I audible? Okay, some disturbance is there. Is it okay now? What about the background noise? It is okay now, or still it is there? Okay, okay. So we are going to start this. So as I was telling, yes, as I was. Hello, is the voice clear now? Okay, okay. Thank you, Arunava. Okay. So as I was telling, yesterday we discussed the basics of the theory of asymptotic analysis of algorithms, and we and we went through different jargons that we come across while analyzing algorithms for their complexity. A brief recap of what we did yesterday in the starting Okay, still the disturbance is there. Okay, when you raise the voice, background noise is coming. Okay, what about now? Light disturbance. Okay, okay, okay. So let me start with that. Okay, okay. Thank you, Gaurav. Thank you, Gaurav. Thank you, Gaurav, for the input. So, as I was telling, yesterday we discussed what are algorithms, why do we need to compare algorithms. Compare algorithms in the sense is that which algorithm is better and which algorithm is a bit slower. So, how do we analyze that? So, we took into account. So, as I was telling, a quick recap of what we did yesterday was we majorly focused on the prime topics that are required, for understanding of the algorithm analysis. Okay, not audible. Still, it is not audible. What is happening? I guess it is fine from my side. Can anybody respond? Am I audible or not? Okay. Thank you, Sumit. Okay, let me just. Uh, Give me 1 minute, sir. I'm a bit confused with the comments right now. Somebody is saying I'm not audible. Somebody is saying I'm audible. Day-2.
How much time does your job search take? 3, 4 months? Even more? Months? Even more?
Okay, I think so. It is audible now because uh, I can hear it. Okay, okay, okay. So let us start. So as I was telling, yesterday what we discussed was how do we analyze algorithms. Given that we have some, we have two algos, algo one and algo 2. How do we see which algo is better than the another algorithm? Then we saw how do we compare in the same algorithm itself, in the same algorithm itself, with the increased size of the input space. And is the input space here, we saw the algorithms perform differently with different sizes of the input size. like suppose like this, something like this, and there we can get some kind of threshold here. Okay, and then we analyzed some scenarios, case scenarios for an algorithm that we termed as best case, worst case, and average case. Okay, then we went into analyzing. Then we went into analyzing how do we see which one is the best case scenario, which one is the worst case scenario, and the journey to took us to. Can anybody respond? Where did we went from here? Can anybody respond? Where did we go after this? We went to the asymptotic notations. Asymptotic notations. That was big O notation, the omega notation, and the theta notation. We discussed these three notations in brief, and then we went on to study what is lower bound of an algorithm and what is the upper bound of an algorithm. Okay, so let me just give you a brief idea of all this in short for the people who are joining today. Suppose I have an algorithm which is used to search an element in an array. Okay, now just imagine the array is something like this: 5 4 3 2 1. The array is something like this. And suppose I have to search a number. The search key is 5. Now the algorithm suggests you take the search key, compare it with every array element one by one, and if in either case, if in any case, if you found the element, if you find the element, you print found, and if you cannot find the element, you print I cannot find the element, not found the element. Okay, now if my array is this, and the search key is 5, in the first iteration itself, the output will be found and the algorithm will behave perfectly. Okay, and the time, suppose each iteration takes 1 second to execute. Now what time does this algorithm takes to execute? It takes just 1 second, the fastest way possible. But now suppose the search key is 2. Now what? Now while searching, it will search it with 5, not found, 4, not found, 3, not found, and then we come across 2 and the search key matches, and we will return found in this case. Now if each iteration takes 1 second to execute, to find 2 in the given array, we had to execute it 4 times. So it took something around 4 seconds. Now the same algorithm which took 1 second to solve the previous search key takes 4 seconds to search the same, 4 seconds to search another key. Now suppose somebody entered the search key as 75. We searched it with 5, matched it with 5, not found. We matched it with 4, not found. Matched it with 3, not found. 2, not found. 1, not found. The array is ended. There is no more element left in the array, and we have come to the end of the array. Still no element is found. And suppose each iteration takes 5 seconds to solve, 1 seconds to solve. So this search took 5 seconds, and still the answer is a not found. Now what we are getting here is the same search algorithm. The algorithm is the same. Iterate over the array, and if the element matches with the search key, return found, else return not found. The algorithm is the same, but for a key that was 5, it took 1 second. For a key that was 2, it took something around 4 seconds. And for a key that was 75, that was equal to 75, it took 5 seconds and then returned no, not found. So what we are getting here is the same algorithm for the different input values executes in different times. Okay, and this is what we name as the worst case behavior, the best case behavior, and the average case behavior. As you can understand, the best case is I have to search an element in the array, and the first element of the array is the search key. So I do not have to iterate through the entire array. And this is what is the best case scenario. The worst case scenario is the element to be searched is not present in the array. And even if we iterate the whole array, we will not find the element. So the worst case is we have to iterate the whole array. An average case is anything that is lying between the best case and the worst case, between the first element and the last element. So a general thumb of rule, as you all might have guessed, while designing algorithms for a given problem, what should we consider? The best case scenario or the worst case scenario? Kindly respond in the comments. Should we while designing an algorithm, suppose I have designed an algorithm to search an element, okay, a modification over the current algorithm, and I present to you this is the best case scenario of the algorithm, this is the worst case scenario of the algorithm, and this is the average case scenario of the algorithm. While designing, which one would you undertake? The best one or the worst one? Okay, well, stay home, stay home, stay home, stay home. Okay, Sumit, we are staying home itself. We'll consider the worst case scenario. Okay, Shivani. Okay, thank you. Okay, so you all understood. We will always take the worst case scenario. Now, while analyzing the algorithms for worst case or best case, we have something known as asymptotic notations. Okay. That we discussed yesterday. Now, we have something known as asymptotic notations. What are asymptotic notations? Asymptotic notations are basically while measuring the efficiency of an algorithm, of the designed algorithm, we cannot depend upon the machine, as I discussed yesterday, because an i5 machine will run a code faster than a code to DO machine. That is a case. Similarly, we cannot rely upon the programmers. There is a programmer named Ram who can code better than code faster. His typing speed is fast than a coder named Rahul. So we cannot take the typing speed of the programmer in concern. Similarly, we cannot take the language. Either I am using C++ or I am using Java or I am using Python. If I am designing an algorithm, it should be language free. So, and similarly, there are many other constructs like the lines of the code or anything else. So we are not considering any of the following while considering while comparing algorithms for betterness. What we consider instead, how are, let's say we have an algorithm, we provide it with input, it provides us a solution. We are interested in how does the algorithm behave, what is the behavior of the algorithm with the increasing input sizes. Okay, and we are mainly interested in this because we do not know that in real world what will be the input size that the algorithm has to deal with. And so we have to provide a range. From this to this range of input sizes, the algorithm behaves in this pattern. From this to this, the algorithm behaves like this. Then from this to this, the algorithm behaves like this. So this is what we can understand. And asymptotic notations help us to understand it better in terms of mathematical notations. And what are asymptotic notations? What are asymptotic notations here? Suppose I plot a graph. I plot a graph of input sizes on the x-axis, increasing input sizes in the x-axis, and performance on the y-axis. Now suppose my algorithm has been modeled into a mathematical function named function of n, where n is the input size and f is the function that we have computed over it. Function can be anything. Let's suppose the function is something like this, n4 plus n cube. This is ff, for an example. Okay, function can be anything based on the code that we have written. Okay, it's a pseudocode that we have written. So function can be anything. Suppose that our algorithm can be modeled into a function named fn, and we plot the performance of the function, efficiency of the function on a graph with compared with the increasing input sizes, and the graph looks something like this. Say something like this. Okay, this is the graph of our function. Now what we do is we have some standard functions. What are standard functions? Like this is the graph of a constant. We all know. Like if I tell you k equals to 2, draw a graph for k equals to 2, and suppose y-axis represents k. So k equals to 2 will be here, and this will represent the constant graph. Similarly, this is a linear graph. Y equals to mx plus c. We all have studied this in standard 10th. Okay. Similarly, this graph is of a polynomial. Suppose something like this. This is an exponential graph. So these we can consider as standard graphs. Now suppose I plot a standard graph here. One standard graph whose performance is slightly better than our function, and one standard graph like this. Let us suppose I call this graph as gn, and this graph, suppose I call it as hn. Okay, now a common aptitude can tell that our function is behaving something in between those, something in between gn and hn. The performance lies between these two. It is better than some and worse than some. Okay, worse than one of the following and better than the one of the following. And what does that both of them represent? One represents the lower bound of a function, of our performance. Our performance can degrade. Our performance will degrade, but it cannot degrade further than its lower bound. Just remember this. What is like we are talking about the worst case scenario. Okay, so what is the worst case scenario? Worst case scenario is we get the highest possible input space. Okay, we get the highest possible input space, and our algorithm's performance degraded by a large value. Okay, but what is the worst case? A worst case scenario is our algorithm cannot behave more worse than that. If I am telling the worst, this is the worstness graph of our algorithm, and the worst case lies here, something like this. So our algorithm can perform like till here, till here, till here, till here, but it cannot perform more worse than this limit. This is the worst case scenario. Something like if I bound it, this is the bound of my algorithm, performance bound of my algorithm. It cannot behave worse than this. Similarly, there was a best case scenario in the search algorithm when the first element was itself the search key. So there is also a bound there. Our algorithm can perform better. This is the better bound. This is the best case scenario. Our algorithm can perform worse than this, worse than this, worse than this, but it cannot perform more better than the best case scenario. Okay, and this is also a bound of our algorithm. We will also bound it. Okay, this is the bound. Our algorithm's performance lies between these two bounds. This is one bound, this is one bound. Our performance cannot degrade below the best case, increase below the best case, and cannot degrade above the worst case scenario. And it always lies something between this, and we call them as average case scenarios. And as you all already told me a few minutes ago, that we are only concerned with the worst case scenario while designing an algorithm. So there is a notation that we call as big O notation, represented as a big O. Okay, and we put inside the O the performance metric of our algorithm. And what it represents is suppose, let's go back to the original graph that we had. We have a graph here. This is our function. Sorry. Just excuse me. This is the graph, okay, of a function. Okay, now this is our graph of our function fn. Okay, something like this. Suppose this goes like this. This is a function of our algorithm. Okay, and there is another function gn, okay, which goes say something like this. This is our gn. Okay, now what we can see here is below this line here, just here, this is the threshold value. We can just tell this as a threshold. Let me write it here. Below this threshold, the performance of our function is sometimes below gn, sometimes above gn. But after the threshold has been crossed, the performance of a function is always below gn. So what we can tell? Let me denote this threshold by a value called n naught. Okay, this threshold is represented by a n naught. So what I can say is, if my n increases above n naught, if my what I can say is, if my n is greater than n naught, then if my n is greater than n naught, and let us consider equal to also. If my value of the input space is greater than some threshold n naught, then the performance of fn will be always lesser than, or let us consider greater than, some gn. And let me give it here a constant here. Let me give a constant here too. Okay, so what I can say is, the performance of a function can degrade, but it will never degrade below the performance of a gn. Performance of gn, if given the input space is larger than n naught. We cannot say anything about when n is less than n naught, but we are certain that when n is greater than n naught, the performance of a function, of our algorithm, will always be below the performance of gn. And thus we can say that gn represents something as the worst case. What we can say, in the worst case possible, then also Fn will be equals to Gn, but it will not become more worse than Gn. So what we can say is Gn represents the upper bound of the function. Gn serves as an upper boundary. It represents at the upper bound. It bounds the function in the degradation range. You cannot, you can degrade. I am limiting you, I am allowing you to degrade further, but you cannot degrade after me. I am your bound. I am the limit up to which you can degrade. This is what Gn is. And so what we tell that the performance, the complexity of Fn is nothing but big O of Gn. This is what we say. Because Fn is degrading. Performance of Fn can degrade, but it will not, it can never degrade below Gn. This is what big O of n represents. Okay. Now, there are other things like omega notation. What omega represents? This represents the lower bound. And now what is the lower bound? You can perform better, but you cannot perform better than the omega. Suppose there is written that a function has a omega complexity of n square. What does this represent? This represents that the function can perform better. The function can behave in n cube, can behave in n to the power 4, but it can never perform as an n. It cannot perform better than n square. This is what omega of n square represents. Similarly, if I write something like this, a function has omega representation, omega complexity of n square, and a big O complexity of say n to the power 4. Now what does this represent? This represents is that the function can behave worse. It will degrade, but its performance will never degrade below n to the power 4. It will never go below n to the power 4. This is the limit. This is the limit. N to the power 4 is the limit. Below, performance can never degrade. And n square is the lower bound. The performance can increase in this range, can decrease in this range, but it will never increase farther than n square. The performance can never be a omega of n or O of n. Let me say, it cannot be compiled in linear time. It will be compiled in polynomial time only, the best case possible solution. And any complexity that lies between omega and big O is represented as a theta notation. Theta represents the average case scenario, average performance of the say our algorithms. Okay, so this is what we know about, this is what we should know about the notations. So while designing algorithms, we are not concerned with the omega notation, we are not concerned with the theta notation, we are only concerned with the big O notation, because big O represents the worst case scenario. It bounds the function in the upper bound, and thus if I have a big O notation of n square, I'm certain that a performance cannot degrade below n square. And if I have the limited resources for n square algorithm, I'll supply that algorithm to the client. This is what we should know. Now, one thing that we should take care here is how do we calculate the different algorithms? How should we compute the big O of n, big O? What is the complexity of an algorithm? How we compute that? So we discussed it yesterday too. There are different kinds of basically complexities that we should know, and the complexities lies in some range. Let me put it here for you. Yeah. Okay. Let me. I just want one thing here. The cutting tool. Okay, this is. It's not happening. Sure. Okay, it is not coming here. Let me write it for you. So the order goes something like this. Uh, O1 is the best possible, best solution that we ever get. Okay, O of log n is the next best that we should aspire for. On is slightly better than this. Then comes the on square. Then O of n cube. Then O of n to the power something. Let me call it O to the power n k. Then O to the power O of 2 power n. And then the worst possible case is n factorial, O of n factorial. Now, what are all these? There are some terms associated with each of the following. Like when the solution is of O1, we call it as a constant solution. This is the best thing that we should always aspire for. Log n is logarithmic. O of n is something that we call as linear complexity. N square is a quadratic. This is cubic. Nk is a polynomial. Nk is n to the power 4, n to the power 5, n to the power 6. N square and cube are all n to the power k only. I like polynomials. Okay, to the power n is exponential. This is the worst possible thing that you can get in your algorithm. N factorial we get sometimes, but we should never aspire for this. We are done. Okay, so this is the best one that we should always aspire for while designing our algorithms, and this is the worst. We should never aspire for this. If our complexity is in polynomials or say factorial or exponential, then we are gone. Just remember that we should always aspire to bring down our complexity to a constant or a linear one. Okay, let me just finish it. Yes, to the power n is exponential. N log n, log n. Okay, somebody is asking what is n log n. See, we have a O of n. We have a O of log n. Okay, just compare both of them. Log n is better than n. We know this. Now, there is n log n. What is n log n? N log is nothing but n into log n. So where should it lie? It is definitely bigger than log n because it has a log n component along with an n component. This is bigger than n because it has an n along with the log n. So the it will go something like this. Log n is the best. Sorry, I should not write this. You said use this one. N and then n log n. Why? Because this is just n. This is n multiplied with log n. Now you will say, what is log n? There is something known as log n or log n square, where it will lie. If you have any confusion, just take some values for yourself. Let's suppose we take 1000 for example. Suppose n is equals to 1000. Input space is of 1000. Now compute. What is on? On is nothing but o of 1000. What is log n? Log n is o of log of 1000. What will be the value? I think this will be 3. Okay. Similarly, what will be n log n? N log n will be something like 3000. And what will be root n? Just compute it and just place the numerical values of the complexities. If you have any confusion, which one is better? If you cannot think in terms of n, just think of an example. Think of a number like 10 lakh, 10,000, 1,000, and just put it in place of n. Compute the numerical value, arithmetic value of the complexity, and just place it. Do arrange in the increasing order or decreasing order. And you can get the complexity in your place in just matter of seconds. It's not a big thing. Now, let's go. Now, the next topic is this is what we did yesterday. This was just a recap. Recap took a bit longer. Okay. I think it is clear with everybody. If you all can respond with anything, yes or no, it will give me a go ahead for the next topic. Sure. Let us start. So, while computing Sure. Okay, so now we'll go into the next topic, that is how do we analyze different codes for their complexities. And today what I will do is I will present to you some questions and you will have to solve them. Okay, now let me just type in something. Suppose there is a loop which looks like this. Okay, the loop looks something like this, and there what we have is a C out of question. Okay. Now just tell me, what will be the complexity of this one? Okay, I'm increasing the font size. I think, how should I increase? Is it visible now, Abhishek? Okay. Now, what will be the complexity of this code structure, like right down here? So, how do we compute the complexity? What we take into account is the size of the space that we are going to get. Okay. So, what we can think is, okay, there is some mistake. Let I equals to, here it should be I equals to say 1. Okay, one mistake I typed here. So, what we can think is I is going from 1 till m. Okay, so I'll be increasing like this: 1, 2, 3, 4, and so on till m. And if each iteration is counted as one complexity, like let's suppose if I have to just print something, see out something, this is what we call it as a constant complexity, O of 1, because we are just taking one unit of something. So this is taking something like O of m. Somebody is responding in O of n. That is also cool, because O of n m is same thing, but we should always answer in the terms of the variable that is given here. Okay, and out till here. Now this is what O of n is there. Now this is a simple one. Now look forward to this one. Now see what I am doing here is a see out again. So I'm doing just see out TW4. Okay. Now what will be the complexity of this thing? Anyone? What is the complexity of this code? Write down here. No, this is not O of n square. Somebody has written as O of n square. See what is happening here. One loop is there from, sorry. One loop is here from here to here. This is taking O of n to execute. Another one is from here to here, and this is taking O of n. So the overall complexity is nothing but O of n plus n. We can say something like this. This is O of 2n. And while considering the, because we already have a component like this, while I was teaching graph, you might have remembered. C into gn. I wrote something like this, if you remember. So this is what we can write it as 2 into O of n, which we can neglect. 2 we can neglect, and the overall complexity comes out to be O of n. Okay. Now, just remember this. N plus n is not 2n. It is 2 into O of n, because the overall concept goes like this: constant into the complexity function. Okay. So this is what we have here. 2 into O of n, which we can just say it because our fn, what was our fn? Fn was less than equals to c into g of n. So this is what we can call it. Our fn is nothing but O of n here. Okay. Now, if I just change the code a little bit, I change the code a little bit here. Okay. What I do is I bring these two lines inside this for loop. Now what will happen? How did this code change? How did the behavior change here? The behavior changed here in this fashion as now what we have is we have a loop outside here, and inside this loop we have a loop here. Now this loop will on itself take O of n time to compute, and this loop takes O of n time to compute on itself. But now the function changed something like this: O of n into O of n, because the n is, because for every I here we have an entire loop to run down here. For 1 it will run for n times, for again for 2 it will run for n times, for 3 it will run for n times. So for every outer loop, n values of outer loop n, it will run for n times. So this is n into n, which comes out to be O of n square. Okay, now this was a simple one yet. Now if I change it a little bit more, suppose I, instead of this plus here, there is a multiply sign, and this loop is not there. Now how is it behaving? What will be the complexity of the function of the loop? Anybody? O of log n, somebody has told. Okay. Now see, what we should consider while getting the, no, it is not O of n. Many people are saying it is O of n by c. It is not like that. How? See, in starting only I said key, while looking out for the complexity of an algorithm, we should look for something known as a space. What is space here? It is not space complexity. It is just something like key. We should know how many spaces we will use, how many iterations it is going to use. So what we can think is, when I was iterating from 1 to n, it was taking n spaces. Okay, but here it is iterating from 1 to n, but the value is incremented in some order. Let's suppose this is not c, for example. Now this is 2. Let's just say this is 2. Okay, what is happening here? For the first I, the value of I is 1. For the second one, the value is, for the third one, the value is, fourth one, the value is 8. Fifth, the value is in this order itself. Okay, so what we are seeing is it is increasing to reach n due to this funda I into 2. The search space has been reduced by half. While I was traversing for n path, okay, now I am just covering it the half path. Okay, so this is what stands out for a logarithmic complexity. Whenever the loop is coded in such a way that the loop variable itself is being multiplied or is being divided by a constant amount, so the search space is divided by that constant. Search space is divided by that constant. Here, let us say that constant. And when the search space is divided by the constant amount, we say that the complexity is of a logarithmic complexity. And somebody well said, log n base c is there. So what is the base? We all know that log has 2 components, base and exponent. So this is the search space, the input size n, and the base will always be the constant value by which the search space has been reduced. And this happens in both the cases. for both multiply and for division symbols. Just remember, whenever there is a multiply or a divide symbol in the loop step counter, whenever there is a increment or decrement value that has a multiply or a divide here, just get to know that the complexity will be a logarithmic complexity here. If it is plus or minus, the complexity will always be of n. If it is a case of nested loop, so it can go to n square, n cube, anything, but the complexity will be n, because the subspace has been not divided. Subspace is not divided or increased. The subspace is the same. Okay, just remember that thing. Okay, no, 2 into n is the wrong answer. Now, hmm, now a very important thing. Sometimes the algorithms are coded in such a way that we cannot solve it. Uh, Suppose there is an algorithm. Okay, okay. See what I am going to tell you. Sometimes it happens is, now what we can do. We have some constructs, like we have if else, we have loops, we have something, some how we get the log. Okay, okay. Uh, how was the value behaving there? The value was going like this: 1, 2, 4, 8. You remember the value was going like this. If I was multiplying, the value was something like this. No, if I equals to I into 2. So if I is 1, the value is 1. If I is 2, the value is 2. If I is 3, the value goes into multiply with 2 and becomes 4. 4 goes into multiply with, it becomes 8. Then before 5 it becomes 16, something like this. Okay, now what we can tell, this is something like this: 2 power 1, 2 power 1, 2 power 2, 2 power 3, and so on. Okay, for some value at the kth iteration, that is only I am telling. Why are we taking the log? See, just come down here. The loop has a increment decrement value as I equals to I into 2. Okay, so for the first iteration the value of I was 1. For the second iteration the value of I was 2. For the third iteration the value of I was 4. For the fourth iteration the value of I was 8. For the fifth iteration the value of I went on to become 16. And thus we can just formulate a series here: 1, 2, 4, 8, and something like this. And what is 1? 1 is nothing but 2 to the power 0. 2 is nothing but 2 to the power 1. 4 is nothing but 2 to the power 2. 8 is nothing but 2 to the power 3. 16 is nothing but 2 to the power 4. We can say this. Now, let's say at the kth iteration, what will be the value of here? What will the value? The value will be something like 2 to the power k. Okay, it will not be k, it will k minus 1, because we have started with 0. Okay, for both the cases the value will be same. Let us take k for the kth iteration, the value will be 2 to the power k. Okay, and the 2 to the power k can be equal to n when k is equals to n, and when 2 to the power k is equals to n, let me take log on both sides, and this becomes log n equals to log 2k. K log 2 becomes log n. Now log 2 is nothing but 1. Okay, so this becomes k equals to log n, and thus we are getting the complexity as log n, because the subspace has become log n. Any doubt till here? Sure. So what I was telling is, currently we were looking at the constructs, the loops, the if-else, the switch cases, and everything else, and we can just infer whether the complexity is O of one, O of n, log n, or anything, something like that. Okay, by just looking at the search space. But sometimes it happens that we cannot just create the search space here. Okay, like suppose I am writing a function here. It is func. It is taking an input n and it is returning, say, the call to the same function by decrementing the value, and there is a constant key if n equal to 1, return 1 else. Now what will be the space of this thing, this particular code segment that I have written here? This is nothing but a recursive function. Okay, this is the recursion, and what is happening here is, if the value of n is 1, then it is returning 1, it is getting executed in O of 1. But if the value of n is not 1, then it is again calling the function, and then again the function getting called from here. And then again, if the n minus 1 is 1, then it gets executed in O of 1. Otherwise, it is again being solved. It is again being solved. It is again being solved. So what we can say here is, the complexity of this particular, the main function, is dependent upon, or it is something like O of n if it gets executed, or it is dependent upon the complexity of the n minus 1. Okay, best case is O of 1, that is only I'm telling. It is O of 1 or the complexity of the time taken for execution of n minus 1. But what is O of 1? O of 1 is the best case, so we will never consider this, as we already know. We already consider the worst case scenarios. So T of n is nothing but T of n minus 1. We are getting something like this. And this is what we call as recurrence relations. What are recurrence relations? Recurrence relations are nothing but when the complexity of outer is dependent upon the complexity of the inner, or a function is dependent upon the value of another function, then that is what is known as recurrence relation. Okay. And whenever we are when are we getting recurrence relations? Whenever we are dealing with anything that has recursion in it, or say repeated iterations in it, then we will always get recurrence relations. Okay, and then what will be the time complexity of something like this? When I am getting T of n is T of n minus 1, how can you say what is the complexity of this particular algorithm? When its complexity is entirely dependent upon, and Tn minus 1 is nothing but its complexity will be dependent upon the complexity of n minus 2. And it will go further until T of n is equals to T of 1, and for which the complexity is O of 1. Okay, so this is something we are dealing with here. This is what we call a recurrence relation. Value of outer is dependent upon the value of the inner, and inner is again dependent upon the most inner part, and this is again dependent upon the inner. We will be always going into the depth. We are deeping dive until we reach something known as the base case, what we know in recursions. Then only we will elope out, and we will get the final outcome. So how do we solve such equations? There, the normal loops, normal things do not come into picture. So we have some methods to solve recurrence relations. One of the most famous method is the Master Theorem. Okay. What the Master Theorem says, whenever you have a recurrence relation in the form of this, T of n is A of t n by b, okay, plus some function, with the conditions that A is always greater than equal to 1 and B is always greater than 1. B is always greater than 1, and B is always greater than 1 because and this represents, if B is always greater than 1, then T will always be a fraction here. N is some number, so if B is greater than 1, it will always be n by 2, n by 3, n by 4, something like that. So a common thing to identify any master theorem, any recurrence relation that can be solved using a master theorem is there will be some number here, there will be T, and there will be fraction inside this, and there will be something, say theta of m here. So this is the what a common click point. If you get any recurrence relation in this form, there is a Tn outside and you are getting a fraction inside. Okay, in our case, what was there? It was T of n equals to T of n minus 1. There was no fraction involved here. Even if we consider fraction, the bottom line will be, the denominator will be 1, and the condition clearly says B is greater than 1. So one common thing to identify whether we are going to use master theorem here or not is key the inner T will always have a fraction here, always have a denominator here, and this is what is the representative. This is what is the clear identification mark of a recurrence relation that can be solved using a master theorem. Okay, just keep that in mind. So master theorem can be applied to any recurrence relation that has a form something like this. There will be A, there will be T, and I clearly said this will be a fraction because B will always be greater than, this B is always greater than 1, and this A is always greater than equal to 1. Just remember this. So it may be present, may not be present, because if not present, it is always 1. So it may be there, may not be there, but here it will always be a fraction, and then again here it will be a function. Okay, so while dealing with master theorem, while handling master theorem, we identified like there are some recurrence relation, like see we have a recurrence relation in this form, T of n by 2 plus say 1. So we can solve this one. I know if a recurrence relation is something of this form, T of n by 5 plus 7, this is also I can solve because A is 1 here, and the theorem clearly says A should be greater than equal to 1, and there it is a fraction, and B is 5 is there, and 5 is surely greater than 1. So we can apply master theorem here. So clear identification of any recurrence relation that can be solved using a master theorem is inner T should have a fraction here. Just remember it. Now what we are interested here is, after identifying whether we can solve it with using whether we are capable of solving it using master theorem or not, now we can identifiable master theorem solvable equation is here, reconciliation is here. Now what we should take into account is this Fn. We are interested in this Fn. What is the structure of this Fn? If this Fn, see condition number 1, if this Fn looks something in this form, O of n to the power say c, which is n to the power c, it can be O of n square, it can be O of n, it can be O of n cube. So what are we dealing here is, if the function is a polynomial function, if the function is a polynomial function, then if the function is a polynomial function, then what are we interested here is, we will calculate a value which will be log of a base b. What are we interested here is, we will calculate the log of the constant out here and the denominator of the fraction here, and let's call it, this value is something c, this value is c. Okay, let me sorry, this log a by b is something, let's say c is already there, let's say it is d. Now what are we interested here is, we have a constant here, the polynomial exponent here, and something here. So what are we interested here, what is the matter of interest here is, what is this d, is it less than c, so is it greater than c, or is it equal to c, or is it less than c? These are the three conditions that we are interested in. First condition, second condition, third condition. Again repeating, whenever we have a recurrence relation, we will first identify it, whether it is a recurrence relation where master theorem can be applied. And how to identify that sort of a recurrence relation? By identifying that the inner T will have always have a fraction, n by 2, n by 3, n by something. Okay, this should always be greater than 1. There can be a number out here or not, and a function will be there. Now what we will do is, if the function addendum function, if it is having a form of polynomial form, if it is having a polynomial form, then we will note down the exponent of the polynomial, whether it is 2, 3, 4, 5, 6. Then we will compute a value d, which will be equals to the log of ab, where b is a base b, where b is the, what is b here? B is the nothing but the fraction. Sorry. B is the fraction out here, the denominator of the fraction, and a is the constant out here. So we will compute log a base b here, name it as d. Then we are interested in whether our d is greater than the polynomial exponent, it is equal to the polynomial exponent, or it is less than the polynomial exponent. We are just interested here. Okay, now if a d is greater than c, the complexity of the recurrence relation will be, let me write it clearly on there again. If d is greater than c, then the complexity will be nothing but the theta. Theta represents the average case of n power d. Theta of n power d. Second case, if a d is equals to c, then the complexity will be theta of n power c, the original exponent, into log of n. If our c is less than d, then the complexity will be theta of the function of n. Theta of the function of n, the original function, whatever was available there. This is a simple thing. This is what master theorem is. Nothing much. There are only 3 steps involved. First is the identification, whether the recurrence relation can be solved using a master theorem. The identification is just, it should have a fraction out here in the t part, inner t part. Then what we will do, we will compute this d. This d is nothing but log a base b. A is the constant multiplied with the inner recurrence relation in inner recurrence, and b is the denominator of the inner complexity. We will compute the log of that. If that log is less than, greater than, or equal to the original